So in our last lesson, we went over conservation of momentum, but only in one dimension. And of course, I can't make it that easy on you, so I need to bring it into two-dimensional conservation of momentum. If something goes off at an angle, we need to be able to analyze that using our X and Y directions. Because if momentum is conserved, then it's got to be conserved in both your X and Y directions. It's not just going to be conserved in one and not in the other. And so, of course, we need to break it down into what's happening in the X direction, what's happening in the Y direction. And so we look at those separately. So there we go. We have our momentum being conserved in the X direction, where the sum of the momentums before in the X direction is equal to the sum of momentums after in the X direction. And then, of course, the same for the Y direction. Now, how do we get things into X and Y direction if it's actually going off at an angle? Well, of course, we need to use trig, our handy-dandy SOHCAHTOA, of course, to figure out how to break this down into X and Y. You guys should obviously be experts in at this point. And so if we're given something going off at an angle and we have the angle, then we should be able to find the opposite and adjacent sides. Or if you want to use Pythagoras, you can also do that. And especially we're going to be using Pythagoras to find the final momentum or the final velocity or final something like that. Okay? So there's not much else to say other than let's just get right into it. So here's an old diploma question that we can go over, where this one's kind of nice and easy, where we'd still definitely have two dimensions, but we just have one going in the X direction and one going the Y. So we have a 2-gram lump of clay moving north at 4 meters per second, collides with another 2-gram lump of clay moving east at 6 meters per second. So we know, of course, when they collide right here, they're probably going to go off in this direction somewhere at the angle. We just don't know exactly, right? Because they're going to collide. Because they're clay, they're probably going to stick together and they're going to go off together in that direction. So we need to figure out what would their final velocity be. Or it says, which of the following diagrams shows the momentum, actually the whole momentum of the system immediately after the collision. So in here, I need to actually use trigonometry to help me do this. So I need the momentum in the X direction, the momentum in the Y direction. However, this one's a little bit easier because, again, I'm not having to break down their individual momentums into X and Y directions, because here we just have one in the X direction and one in the Y direction. So I'll call this lump A and this lump B. And really what's going to happen is the momentum of lump A is going to be going there to the east, and then we can get the momentum of lump B, which is going north, and find our resultant momentum right there. Okay? And that's all we're going to do. So since we can actually find the momentum of A and find the momentum of B, here I can just use both of those to find the total by using Pythagoras. Oopsie. So that's what we're going to do. Let's go right into Pythagoras. So, of course, that total right there is just going to be the square root of momentum A squared plus the momentum of B squared. How do we find momentum? Well, that's mass times velocity. So that's mVA squared plus mVB squared. And then we can plug in our numbers. And we do that, we get a total momentum of 14 kilograms meters per second, okay? And so if we look at our options in the multiple choice, and we're looking for one of the ones that says 14 kilograms meters per second. So it's obviously C or D. And then we just need to figure out what the angle would be. So that would be this angle right here. Now, of course, we can actually figure out the angle using the tangent of theta. But also, I think in this one, you can probably reason out which angle it would be. Even before you even do anything, we could probably also rule out A and B, just because we know this isn't going to go off at a 45-degree angle, right? We know this is not going to be 45. Why is that? Because A has more momentum than B, right? Because it's going 6 meters per second, not 4. So we already know A has more momentum. So we can also probably assume that this angle right here is smaller than this angle. Okay, so let me say that again. We can assume that this angle made with the horizontal is smaller than the angle made with the vertical, because we know, of course, that the one in the x direction has more momentum. So this is going to go more horizontally than it is vertically. Okay, but let's actually calculate the tan of theta just to double check and figure out which angle we have here. Okay, so tan of theta would be the momentum of B divided by the momentum of A, which of course is mass of B times the velocity of B divided by mass of A divided by the velocity of A. If you don't do this, we can cancel the masses since they do have the same mass. If you don't remember to do that, nothing's going to happen. You're going to be completely fine, but we still can do that. So my angle is going to be the inverse tan of the velocity of B, which is 4 meters per second, over A, which is 6 meters per second. And so that angle there is 34 degrees north of east. Of course, we don't actually see 34 degrees in either C or D, but we see the complement of that, which is 56 degrees east of north. So therefore it must be D, because of course if that's 56 degrees, then this angle right here must be 36 degrees. And there we go. Okay, so that's a nice easy example of momentum in 2 dimensions, because again, we're not having to take our individual momentums and break those into x and y yet. We just have one going the x direction and one going in the y direction. So let's do an example where now we have to look at something that is going off at an angle, and we have to then break it into our x and y. Okay, so here we have a white billiard ball traveling west at 13 meters per second, strikes a stationary green ball. If the white ball has a final velocity of 4.5 meters per second at 38 degrees north of west, find the velocity of the green ball. So we know afterwards they're going off at angles. Before, we can assume that there's really no angle, because it just says that the white one's traveling west and then the green one is stationary. So obviously, always best to draw a diagram. I always like to do a before and after when we're looking at 2-dimensional momentum problems, because it just really helps you figure out what the heck's going on. So we got our green and white billiard balls, and of course before, the white one's just going straight west. And the mass of that guy is 0.75, and it's going at a speed of 13 meters per second. Of course, our green billiard ball is stationary, so it's 0 meters per second, and that guy's 0.8. And then after, what do we know? We know the white ball has a final velocity of 4.5 meters per second, 38 degrees north of west. So let's kind of draw that triangle that we need. So 38 degrees north of west would be about like that. Okay, so here's our white ball. And so we know the mass is still 0.75, and the velocity now is 4.5 meters per second, 38 degrees north of west. So I would always just go right ahead and start drawing that right angle triangle, because of course we know here the hypotenuse is the 4.5. That's the actual speed it's going, so that's what it gave us. And so we are going to need to break that into x and y. 38 degrees north of west, that would be this angle right here. I'm going to call that theta w, because it's the angle that the white ball is going off at. Okay. And then we got to figure out what the heck's going to happen with the green ball. Now, because we know momentum must be conserved, there was no momentum in the y direction beforehand, so I know there shouldn't be, like, it should have a momentum of 0 in the y direction afterwards. So the green ball's probably going to go kind of counteract the way that the white ball's going to go. So it's going to go down, or going to go south, I think, instead of north. But I don't exactly know what angle that's going to be at or what that velocity is going to be. Like, we just don't know that, right? So we don't know the angle, we don't know the velocity there, and that's what we're looking for. So I would always recommend kind of drawing out what you have, because it helps you reason out things like that, and then go from there, okay? So in this case, we do have to look at the sum of our momentums in the x direction before and after, and then in the y direction before and after. Because again, what are we trying to do? We're trying to find the velocity of the green ball. This is what we want afterwards. Okay, and it's off at an angle. So what we're going to have to do is we're going to have to find its velocity in the x direction, its velocity in the y direction, and then we're going to have to use Pythagoras to figure out that hypotenuse. Okay, so let's start giving that a try. So again, I'm going to have to go on to a new page here. So we're going to start with the momentum in the x direction. So I also want you to start with this statement. Momentum in the sum of momentums in the x direction before is equal to the sum of momentums in the x direction afterwards. Okay? Before, what do we have? We have the momentum of the green ball and the white ball. So the mass of the green times the velocity of the green ball plus mass of the white ball times the velocity of the white ball. And that's, of course, in the x direction, but that was already in the x direction, so I'm not going to put an extra subscript of x. But now, when I look at the mass of the green ball times velocity of the green ball afterwards, that has to specifically be in the x direction, so you put the extra subscript on there, and try not to get lost in all the subscripts. Okay, so how the heck are we going to get things in the x direction? Before we do that, I'm going to go ahead and just cancel that out, because guess what? Momentum of the green ball before is 0, so we don't have to think about it. But now I want to really look at the fact that I need the velocity of the green ball in the x direction. Actually, I'm just going to get that. But the velocity of the white ball in the x direction, how the heck do we get that? Because we do have the velocity of the white ball. We have the angle it's going at. So, of course, if we look at the x direction here, this is the adjacent side. Okay, if you're looking at this x direction right here. So I should be able to get that by multiplying the velocity of the white ball, the 4.5, by cosine of that angle, because it is on the adjacent side. And that is how I'm going to get the velocity of the white ball in the x direction. Okay, so this guy simplifies to the momentum of the white ball before, which is all in the x direction, times the momentum of the green ball in the x direction, which is what we're trying to find, plus the momentum of the white ball in the x direction, which is, of course, mass times velocity of the white ball times cosine of the angle that the white ball's going off at. Okay, and so that's how we can get it in the x direction, because again, if we look at our right angle triangle, that x direction is in the adjacent side. Okay, otherwise I think we have all the things we need except for the speed of the green ball in the x direction. So let's solve for that. And so the velocity we get for the x direction of the green ball is 8.9 meters per second. Okay, so going back to our diagram here, that's this guy in the x direction, so that guy's 8.9 meters per second. So you see hopefully what's happening is we're finding the x direction, and then we can find the y direction, and then we can find use Pythagoras to actually find what the velocity of the green ball would be. So hopefully you're seeing that so far and kind of getting where we're trying to go with this. Okay, so that's the x direction, but of course we're nowhere near done because we now need to go over to the y direction. So that's what we're going to do. And the sum of momentums in the y direction before should equal to the sum of all momentums in the y direction afterwards. What momentum is in the y direction beforehand? There's none. It's just moving horizontally. So here we know that guy is a big fat 0. Okay. And then, of course, we have momentum of the green ball afterwards in the y direction, plus the momentum of the white ball in the y direction afterwards. And how are we going to get momentum of the white ball in the y direction afterwards? Well, that one's on our opposite side, so we're going to multiply by sine of theta, so it should be 4.5 times sine of theta. So that's what I'm going to put in for the velocity of the white ball afterwards, is the velocity of the white ball times sine of that angle that the white ball goes off at. And so if I do that, I should be able to solve for the speed of the green ball in the y direction afterwards. Okay, you know what? I forgot to do something because we're just in the in the X direction, we were overwhelmingly just working with the west direction. And so I forgot to define a direction as positive. So the west is going to be positive because I'm overwhelmingly working with that. However, in this one, we might need to look at how are we going to get, something going north and south, because we know green ball's likely going south. So we also need to define a positive direction for this guy. So I'm going to go ahead and make north positive as we normally do, meaning I should get a negative speed. Okay, so that just means that my velocity of the white ball in the y direction should be positive. If I made south negative, that then would have to be negative, that 4.5. Okay, so velocity of the green ball in the y direction would be the negative momentum of the white ball in the y direction divided by the mass of the green ball. Okay, and let's solve for that. And look at that, we do get a negative because, of course, that negative was out there before. If I had made south positive, then this 4.5 here would be negative, and then I'd have a negative times a negative, which would then be a positive. So again, the signs should always work out for you, and if they don't, you've likely done something wrong and missed a sign somewhere, okay? So that, again, that signage does tell us, oh yeah, this is definitely going south, okay? So we have our velocity in the x direction, our velocity in the y direction afterwards. So I should be able to use those two to now use Pythagoras to find the final velocity of the green ball. Okay, because again, this guy is 2.6 here. Now, of course, when you're actually calculating it, please don't use just 8.9 and 2.6. At least use it to quite a few decimal places. I'd say at least 5, just to get the most correct answer. But anyways, I'm going to draw this resultant vector diagram just a little bit bigger over here, where I have the velocity of the green ball in the x direction and the velocity of the green ball in the y direction. So we should be able to just find the velocity of the green ball. Remember, I'm saying velocity, which means I need a direction, which means I'm going to need also this angle. Okay, so we'll start by finding just the magnitude of the velocity by using Pythagoras. Keep in mind that that negative 2.6 gets squared and therefore just becomes a positive. And what we should get is 9.2 meters per second. Okay, so that's our velocity of the green ball. And then, of course, we just need the direction that it goes in. So that actually that's a speed of the green ball. And that we can get the velocity by using tangent of theta. Technically, since we have the hypotenuse, I could use sine or cosine. But I tend to just keep it to the same process every single time, which is using tan because we found that x and y. We did all that work, might as well use them again. Okay, so I should be able to find my angle by using inverse tan of the velocity in the y direction, 2.6, divided by the velocity in the x direction, which is 8.9. And that angle should be 16 degrees, but of course I need directions on that as well. So we know that this 16 degrees is going south and west, but specifically with the way I drew the triangle, this would be south of west. Remember, if you gave me west of south, that'd be fine as long as it's the complementary angle. Okay, which here would be 74 degrees west of south, so either one of those angles would be perfectly correct. But there we go. There is our resultant velocity of the green ball, which is 9.2 meters per second at 16 degrees south of west. Can you believe I have 2 more examples? And they're all like that. So here's the thing about momentum in 2 dimensions. It's a lot of writing, it's a lot of work, and at first it's very, very overwhelming. But as soon as you do like 10 of these examples, you start really seeing the process, you start really seeing the repetition, and it becomes basically just the systemic thing that you just keep doing. And it's actually Not quite as difficult as it looks at first, okay? But let's keep going on a few more examples. Okay, so now we have a car traveling east at 25 meters per second, colliding with a train traveling at 30 meters per second, 20 degrees east of south. So there we go. That one is going at an angle. So again, here I'm probably going to have to break it into its X and Y directions because, of course, the train is initially going at an angle. And that means when they stick together after the collision, they're probably also going off at an angle. So again, the first thing you should always do, though, is draw a diagram, please, and thank you. So before they collide, we have this car here, and he's just going on his merry way, but not noticing he's about to run into a train. We're going to go ahead and assume here that the train, I don't know, for some reason doesn't stick to the tracks, which, of course, isn't probably not what's going to happen, but I'm just going to go ahead and assume it because, yeah, that would be an outside force and then momentum wouldn't be conserved. So we're just not going to look at that for now. Okay, and so our truck is going, 20 degrees east of south, so that's that angle right there. That's a 20-degree angle. So, of course, the train is way, way bigger, so it's probably going to have a more of a effect on which direction it goes eventually, but we know it's going to be going southeast in some way, shape, or form afterwards, right? So when we draw our afterwards diagram, then we have the train and the car kind of stuck together here. Smash. And then they're going to be going off in this direction somehow, some way, but I really don't know how. So I don't know this angle. I, of course, don't know this velocity, and that is what I'm looking for. Okay, so remember the mass of the car is 2 times 10 to the 3 kilograms, which is really just 2,000 kilograms, and that's what I'm going to write. And the velocity of the car beforehand is 25 meters per second. And of course, the mass of the train is 1.85 times 10 to the 4, which is 18,500 kilograms. And then the velocity of the train afterwards before is 30 meters per second. But that's at 20 degrees east of south. So keep in mind, we're going to have to draw our lovely little right angle triangle here so we can get the velocity in the X and Y directions. So again, there's our angle. So at this point, our velocity in the X direction is the opposite side and the velocity in the Y direction is the adjacent side. So we're going to use sine for velocity in the X direction and cosine for velocity in the Y direction, which is opposite of what happened before. And then, of course, we know afterwards they actually have a combined mass and a combined velocity because they stuck together. So here we have the mass of the car and the train afterwards. And of course, that's going to be just the sum of both of their masses, which is 20,500 kilograms. And we're going to have to figure out what the heck is their velocity afterwards. Since it's the velocity of both of them together, I'm just going to call that final velocity at this point because why not? Okay, so let's do this. Let's find the sum of our velocities beforehand, some of our velocities after, momentums in the X and Y direction. So let's start with the X, define our positive direction, which I'm going to go ahead and say is east because I think east is really the only direction we're going. Okay, I'm going to say east is positive, sum of momentums in the X direction before equals sum of momentums in the X direction afterwards, and then we figure out our individual momentum. So we had the momentum of the car in the X direction before, plus the momentum of the train in the X direction before, and that should equal to their combined mass and velocity afterwards. Of course, that's only in the X direction. We're going to have to do both. And in order to get the velocity of the train in the X direction, remember that's going to be the velocity, the 30 meters per second times sine of 20 because it's on the opposite side. So that's going to be sine. And so if we want the final velocity in the X direction, we can just divide both sides by the combined mass of the car and the train. And our final velocity is 11.7 meters per second, at least in the x direction. So we're gonna hold on to that and use that in a bit. But of course, now we have to go over to our y direction and figure that stuff out. In the y direction, we are overwhelmingly going south. So I'm gonna make that our positive direction. Okay, and then of course, we know the sum of momentums in the y direction before should equal to the sum of momentums in the y direction afterwards. Okay, beforehand, the car has no momentum in the y direction, but the train definitely does. I'll still write the momentum of the car in the y direction. Okay, and then of course, how are we going to get the momentum of the train beforehand in the y direction? Well, that is on the adjacent side, so I'm going to multiply that by cosine of theta. And of course, that will equal their combined momentum afterwards in the y direction, which is what we're looking for. We're looking for that final velocity in the y direction, okay? So this guy's 0 because it's not moving in the y direction at all. It's only moving east beforehand. But of course, we can find the momentum of our train in the y direction by multiplying by cosine of theta. Okay, we get a final velocity in the y direction, 25.4 meters per second. So that just means it's overwhelmingly moving in the y direction more than it is in the x. So it's probably going to be closer to going south than it is to going east. But of course, it's still going to be at a direction. So now that we have those separate components, we can find out what the heck our actual velocity looks like of these two combined things. Because we know it's going south at 25.4 meters per second, but its velocity going east would be going at a rate of, what was it? 11.7, there we go. So there's a velocity in the y direction, the velocity in the x direction. I just realized I drew this triangle. Oh no, this is how I drew it in my notes too. We're good, okay, and then we wanna find the angle and the final velocity just all together. And at this point, hopefully starts looking a lot easier because here it's just a simple Pythagoras and tangent to find the speed and the angle at which it's going. So let's do that. So we get a final velocity, or at least a final speed of 28.0 meters per second. Keep in mind, my question had all three significant digits, so that's what my answer should also have. But let's go ahead and find the angle as well, because we're not done until we find that angle, because it asks for the final velocity, which is, of course, magnitude and direction. So you should get 24.7 degrees, and this one would be east of south, because again, if you start south and then you swing out to the east, you get a 24.7 degree angle. But of course, if you had the complementary angle to this that was south of east, that would be equally correct. Okay? So hopefully you're starting to see the patterns here. Because we really are kind of going through the same motions every single time. But as it is some very complicated calculations, I have one more example to go over with you. If you want to pause right now and try to do it yourself, that would probably be a good thing to try and do. But if you just need help, then of course, watch the solution as you need to. So here we actually have what we call an explosion, because we have an object moving just 17 meters per second north, like a big object, and then it's exploding into three pieces. So in any explosion, the momentum before should still equal to the momentum afterwards, because again, what's happening is you're losing mass in each piece, so it should have a different velocity, but altogether it should still have the same momentum before as it does afterwards. Okay, so what the heck? So before we just have this big mass of something. I don't know what it is, but it's moving north. Okay, at 17 meters per second. So that's, yeah, just before. It's moving at 17 meters per second. I don't actually know the mass yet, but we'll figure that out. Okay, afterwards, we have a 12 kilogram piece moving at 10 meters per second, 65 degrees south of east. Okay, fun. 9 kilogram piece moving 8 meters per second at 20 degrees west of north. And then a 14 kilogram piece, and we don't know the velocity of that third piece. Okay, so I'm going to try to draw these 3 pieces. Okay, so again, we know one's going south of east. I'm going to draw that guy over here. Okay, because south of east is this way, and I don't want it to get into the way of the other stuff. So that's doing that. Okay, and then of course I'll just draw my diagram right now. So that's a 65 degree angle. Okay, and so I'm going to call that was the first piece. So I'm going to call that piece A, just because why not? And also I need a way of keeping track of stuff. So this is going to be piece A. Okay, and the next one I'll call piece B. And that is going 8 meters per second at 20 degrees west of north. Okay, so that's kind of going up like that. And again, we'll just draw a right angle triangle here. Okay, so that's 20 degrees right there. And I'm going to call that piece B, just so I can kind of keep track of all these different pieces. And so then we'll call C the one where we don't know it's going. So I'm going to say it's probably going north in some way because before we were going north, but I don't know if it's like fully north or northeast or northwest. I don't really know, right? We're not too sure of that. And that's what we're trying to find. We're not only trying to find its velocity, but also the direction it's going in. Okay, so, but we do have all their masses. So I know mass of A is 12 kilograms. We know the mass of B is going to be 9 kilograms. And then I'll call this piece C, and that's going to be 14 kilograms. So then I should be able to find the mass of the piece before, because it would just be the combination of all those masses. So we got 12 kilograms plus 9 kilograms plus 14 kilograms. And so that gives us a total mass of 35 kilograms beforehand. All right, you guys ready to do this insane question? So if we're really breaking this down, we can see that there's momentum before in the y direction and in, afterwards, but before in the x direction, there's no momentum. And so, of course, we know our momentums in the x direction afterwards should equal to 0 at the end of the day. Okay, so I'm going to call this just MT and VT for like the total thing. Okay, so again, I'm still going through this exact same motions. I'm going to say momentum in the x direction before is equal to the sum of the momentums in the x direction afterwards. Okay, I'm going to define a direction as positive. So here it doesn't matter, we can have east or west because we know we're going to have a combination. So I'm going to go ahead and make east positive, because when in doubt, just go with your classic east and north as positive. Okay, and so when I'm looking at the momentum of the total piece beforehand, I know that's 0. And then I'm going to look at the momentums of all the pieces of A and B and C in the x direction afterwards. So A, velocity of A in the x direction, momentum of piece B times the velocity of piece B in the x direction, plus mass of C times the velocity of C in the x direction afterwards. Okay, so for A in the x direction and B in the x direction, we can find those by using SOHCAHTOA. So we see for B in the x direction, we have up here, we have that on the opposite side. So of course we're going to take B and multiply it by sine of theta. Okay, and then for A, we see it's on the adjacent side. So we're going to take A and multiply it by cosine of theta. And then C, we're not going to know. So again, the sign that we get for the velocity of C in the x direction is going to tell us if it's going east or west. Okay, so let's do this. We know that's 0. So let's rearrange for the velocity of C in the x direction. And so, of course, that numerator should have a negative all in front of it because we had to subtract mass of A, the momentum of A and the momentum of B. Sorry, so that should be a minus as well. So the other side in order to get the momentum of C all by itself. Okay, so there's our equation for the velocity of C in the x direction afterwards. So let's plug in our numbers. Note that I made the 8 meters per second negative. Why did I do that? Well, because for piece B, it's going to the west, and we made east positive. So that's actually the portion of the velocity for B that's going in the x direction is the negative direction. So I counted for that by making 8 negative. Okay, so really, really important that you note that when you do have a portion going west, even though you're multiplying it by sine of 20 to get it into the x direction, we still need to consider that that is going in a negative direction. Okay, and so our velocity for C in the x direction should be negative 1.9. What does that negative tell us? Oh, it tells us that it's actually going a little bit to the west in the x direction. So that's helpful for us. But let's really figure out what's going on in the y direction, because that's really what's going to tell us what's happening here. Okay, so in the y direction, we know before it does have a momentum going north, and then so afterwards, it should still equal to that momentum going north. Okay, so I'm going to go ahead and make north positive, even though we do still have some south components here, but I think overwhelmingly C is probably going to be going north, so I'm going to make north positive. Okay, same thing. We're looking at the momentum of the total mass beforehand in the y direction, but of course that is just its entire momentum. And then we're breaking down the momentum of the 3 pieces in the y direction afterwards. And again, we're going to do that using SOHCAHTOA, except for piece C, which of course we're just looking for the velocity of C in the y direction. So much to write. Okay. So, can't cancel out anything here. It's going to be a monster of an equation. Just going here really quickly, just to make sure we know how to get the momentum of B in the y direction. That's going to be times cosine theta, because y is on the adjacent side there. And of course, for A, the y direction is on the opposite side, so we're going to multiply A by sine theta. Also, A, the y component of A is going south, which is going to be negative because, of course, we know north is positive. So, again, make sure we're plugging in a negative for the velocity of A because that component in the y direction is going south. Okay, so I should be able to solve for the velocity of C in the y direction here, and it's going to be a big monster of an equation. So try to keep up. But it'll be the momentum of the total thing beforehand minus momentum of A in the y direction afterwards, minus the momentum of B in the y direction afterwards. And then, so that would be times, I totally forgot to multiply by cosine and sine theta, because how do we get the y direction? We multiply by cosine and sine. Okay, so that'd be times sine of theta A minus MB V times cosine of theta B. Oh my goodness. Just getting messed up with all these subscripts. Okay, so let's plug in the numbers for that lovely equation. It's going to be so much fun. I'm definitely going to run out of room. Okay, oh my goodness. So after all that, we can get the velocity of c just in the y direction. We're not even done this question, but we get that that is 45 meters per second, which is fast. So this is pretty much just going north. Like it's going northwest a teensy bit, but it's mostly just going north. But we still need to then use Pythagoras to figure out the exact velocity and the exact direction that it's going at. So I'll go back here or not. Oh, I'll run out of room for that. Just a sec. Okay, so we have our velocity in the y direction being 45 meters per second, and then the velocity in the x direction is just teensy bit to the west of there. That's still probably, I still haven't even exaggerated this enough, but that's okay. And that's our final velocity of c. Doesn't that look fun? Oh my goodness. So let's use Pythagoras. So at least this is the easy part now. Let's use Pythagoras to figure out the final velocity of c. And what do you know? With two significant digits, it still just remains 45 meters per second. So that 1.9 really wasn't enough to get that to round up to a 46. So that doesn't mean that it's going fully north. It just means it's overwhelmingly going north. So we should still find this angle that it's going at, okay? Because it might not be a full 90-degree angle. It will probably be 1 or 2 degrees. And we still need to know that. So we get 2.3 degrees west of north. Again, all our answers need to be in two significant digits since that was what was in the original question. And oh my goodness, I can't believe we're done that. So as you've noticed, these take a lot of work, but hopefully you've also started to notice the repetition. So really once you do like 10 of these questions, they become a little bit less overwhelming and just more tedious in just how much work they need. But again, it's the same work every time. Just be really careful with not missing out on these kind of negatives there and those kind of things. Okay, so just do a bunch of examples on that, and honestly, you'll have it down within doing like 10 to 15 examples of these.